Good evening and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This evening we're looking at using integration to find areas, and I just want to start off with a lazy habit that we as mathematicians fall into. We say that one of the purposes of integration is it finds the area under curves. It's not quite true. It finds the area under a curve, yes, but between the curve and the x-axis. So what I'm going to look at doing in this first example is I'm going to use integration to find the area below the curve with equation y equals x squared plus 3 down to the x-axis between limits of x equals 1 and x equals 4. So I've drawn the graph of the original equation, I've drawn the lines x equals 1 and x equals 4, and I'm finding the area of this region R here, which goes like so, and you sometimes hear these referred to as finite regions. And the way that you do it is that you use integration. So I'm going to start off with the symbol for integration, integrate what's coming. My upper limit is 4 and my lower limit is 1. Now I know that because they're the numerical values that I'm integrating between. I then have the expression that I'm integrating, which is x squared plus 3. And then I have this bit of notation here, dx, which means with respect to x. So what that means is the expression that I'm integrating is x's. At the moment, that's fine. When you come to year 2 calculus, you'll have to deal with, well, what if you've got different variables going on? But at the moment, it's just x's, so we can just power on, integrating as you normally would. So we integrate x squared, we're going to get 1/3 x cubed, and if we integrate 3, we get 3x. Now, once it's integrated, it goes into square brackets with an upper limit of 4 and a lower limit of 1. Now, you may be looking at this thinking, what about the constant he's forgotten plus c? In this case, because it's definite integration between limits, we don't need the plus c. And at the very end, I'll very briefly explain why you might want to think about why that's the case as I work through the next bit. We're then going to evaluate this integral between the limits of 1 and 4. And the way that we do that is we substitute in 4 to this expression here, we substitute 1 into this expression, and we find the difference. Now, to show that that is a different stage of the process, we start now using curly brackets. So we've got 1/3 of 4 cubed plus 3 lots of 4 inside a set of curly brackets. That's going to be my first value. Subtract 1/3 of 1 cubed plus 3 lots of 1. Now, your calculator will do this for you, of course, but I quite like to do each term. So we've got 64 over 3 plus 12. Subtract 1/3 plus 3. So what we have here, we have 100 over 3, take away 10 over 3, 90 over 3, which is 30. So what I found there is that the area of this finite region R below the curve down to the x-axis between 1 and 4 is exactly 30. And it's just 30 units, it's not centimetre squared or anything like that, it's just the value 30. Okay. Going back to why no plus c when we integrated it, well, if we'd had a plus c in here, then we would have had a plus c in here, the same plus c in here, and they would have cancelled each other out to 30 anyway. So when we're doing definite integration for the purpose of finding an area, we don't need to worry about plus c. In part 2, we'll look at another example that we have to set up ourselves.